this system has this property, and this property has to do with order. That is the key word. I haven't told you the property yet. I will tell you that shortly. This property has to do with order. And this property says that, look, you can do 5 plus 8. So 5 plus 8. So here's my 5. Here's my 8. So 5 plus 8 is 1. And this property also says, you know, it's cool if you switch the order, because if you do 8 plus 5, you still get 1. And notice how this 1 is equidistant from this mirror as the other one. Let's take another example. What if I was doing, let's see, 10 plus 2. So 10 plus 2 is right here. And now let's look at 2 plus 10. So I look at 2, I go over to 10, here's 2 plus 10. So the distance from here and the view into the mirror is the same. So this property holds true in this clock arithmetic. This property is called the commutative property. And if there is commutative property. If there is commutativity, then you can change the order and still get the same answer as you see right here. This is 1 and this is 1. So how do you know if a random system actually has the commutative property? Well, let's take a random system. This is a random system I created. It's not a numeric system, but it is a finite system. It has 4 elements. The operation is diamond. I don't know how that works, but I do know if I want to do C diamond A, I would look here, C diamond A, and I would get a B. Now, I'm curious, if I reverse that order, what would I get? And let's look at A diamond C. So A diamond C, I get C. So does that tell me whether this system is commutative or not? That tells us the system is not commutative because I just changed the order and I got a different answer. But wait, Miss Colkin, how are we supposed to guess that C and A is what you looked for, and A and C? You're not. You don't have to guess. What you do is you just take a quick glance. Because if I had chosen B operated with A, here we go, and A operated with B, I would have thought this was commutative. So do I have to test every single part? Oh, that sounds awful. Well, yes, it is. That's why you use this pattern in the table, this trick. So the pattern has to do with mirror symmetry across this diagonal. And so you only are focused in on the table, not the headings. These are the headings. And so I'm only looking, when A looks in the mirror, is this A seeing the same thing? When B looks in the mirror, oh my gosh, can you imagine being B and you look in the mirror and you see C? Like, what if you woke up one morning and you looked in the mirror and it wasn't you, right? So here's an example, the one we revealed, that this is not commutative. Now, take a notice here. D and C are looking in the mirror. C is the closest to the mirror. So shouldn't C appear first on the other side or in the mirror? Yes. So this is an example of mirror symmetry, this one right here. But notice, we just need one piece to mess it up to say it is not commutative. So let's take a look at this. First of all, what system is this? It is the 5 addition. And is this commutative? So I'm going to not focus on this. I'm not focusing on this. So I'm just looking 2 and 2, 3s and 3s, 4s and 4s, 5, 0s and 0s, 1s and 1. Okay, yes, I'm going to say yes, this is commutative. And the reason is there is mirror symmetry across the top left to bottom right diagonal. Mirror symmetry across the top left to bottom right diagonal. And does that make sense that addition is commutative? Yeah, because we think, like, if you add 7 and 3 and 3 and 7, yeah, that's fine. Okay. So here's another way of thinking about the commutative property. This would be wise to have in your notes if you don't already. The commutative property is about order. That is its key word. A system is commutative if you get the same answer when you switch the order. So 4 plus 1 equals 1 plus 4. If that is true, then yes, it is commutative. If 4 plus 1 does not equal, or let's say use a different operation, if 4 heart 1 and 1 heart 4, if somehow, I don't know what, they were different, if they were not equal, then you would say that system is not commutative. And the pattern you look for to test commutativity, if you want to add this to your notes, is mirror symmetry across this diagonal in the table. And a really good question is, why does it have to be that diagonal? So let's take a look here. I don't know how this system works. I know I'm only focusing in on the table, not just the headings. I want to know about commutativity, so I'm looking for mirror symmetry along this diagonal. So when E looks into the mirror, it sees O. That's weird. It's not commutative. Now, tell me, what operation produces this E? So E at L produces that E. Now, what operation produces this E? Well, not surprisingly, directly across from the mirror, or through the mirror, is L at E. But that equals O. Okay, so these are not equal, so this system is not commutative. This is called a counterexample. I just need one to say it's not commutative. There's a bunch of others, like look here. This would be M at L, and this would be L at M. And that's not commutative. So notice this diagonal is really important, because whenever I pick something on this side of the line that's equidistant across this line is so important, because whenever I pick that, so this is O operated with E, O at E, and this is going to be E at O. See, E at O. So notice that's why that diagonal is important, because these cells that are directly across this mirror, this diagonal, are the cells that change the order perfectly, and they perfectly switch it. Last one, is boat commutative? The answer is no. Where is your counterexample to prove that no? That would be T and O. And immediately I know it's going to be O and T. I don't even have to look in my table, but I'll check. O and T. Yeah, so this one's equal to B and this one's equal to A. Those are not the same, so this is not commutative.